Hello everyone, welcome to the tutorial series of Python language quantitative trading practice. In the previous lesson, we have learned about assignment operators, var and varIp, and today we will continue to learn some operators in the Python language, starting with arithmetic operators. There are 5 arithmetic operators in the Python language: addition, subtraction, multiplication, division, and modulo. What we need to pay attention to is most of these arithmetic operators are binary operators. A binary operator is an operator that requires 2 operands, such as addition. An addition operator requires 2 operands, such as a plus b, and assigns the result of a plus b to c. Most arithmetic operators are binary operators, but 2 operators, addition and subtraction, can be used in both binary or unary form. For example, I declare a variable a and assign it the value of -1 here. This is the use form of a unary operator. We can see that this operator has only one operand and assigns the final operation result to a. Similarly, with the plus sign, we assign +4 to b. Which is also the use of unary form. Other operators, multiply, divide, and modulo, they can only be used as binary operators. Otherwise, an error will be reported. For example, we write a test code here. C equals to we use the runtime log function to print out both a and b here. Then we comment out C here. At this point, we click on backtest. It will not report an error. And we can see in the log column, the value has been printed out. Let's see the value of A here, which is -1, and the value of B is 4 here. But if the multiplication sign is used to represent a unary form, here, we click on backtest. You can see it reports an error here. That is, except for the plus and minus signs, other arithmetic operators cannot be used in unary form, otherwise an error will be reported. The plus operator is special among arithmetic operators. For example, when there are non-numeric operands, the plus operator has the function of concatenating strings. For example, here we write C equals to BTC. Plus USDT. That is to say, there are two parts on both sides of the plus sign. This part is added first, and then the latter part is added. The order of operators with the same priority is executed from left to the right. Don't forget to add runtime log C here. That is, we print out A, B, and C. Here we click on backtest. And here we can see on the log message column that the variable C is just a string, BTC USDT here. Therefore, the addition operator is special among arithmetic operators. It is used on both sides of the numerical value and is a mathematical operation. If there are strings on both sides, it is a string concatenation function. Let's explain it through an example here. What the role is when the operands on both sides are different type of values. First, we declare a variable a with two values, 1 plus 1. Then we declare the variable b equals to 1 plus 1.1. And then we declare the variable c. C equals to 1 plus string 1.1 here. C string. And then we declare the variable d. Let it equals to string 1 plus string 1.1 here. And then we declare the variable e equals to e equals to 1 plus NA here. NA means now in the Pan language, and we print it out with the runtime log function. We print them all here. and we click on Backtest. Let's observe the values of these data outputs in the log information column here. We copy the first line of we copy the first row of data here and pass it into the strategy code page. For our observation, we can see that the value of A is 2 here. That is, the addition operator 1 plus 1 performs a mathematical operation. The value of B is 2.1 here. It performs a mathematical operation 2 here. The returned data is not an integer, but a floating point data, C plus string 1.1 here. And the value of C is 11.1. It is equivalent to turning 1 into a string and splicing the two strings together to get 11.1. D is to splice two strings here. It is exactly the same as the result of C, also 11.1. It is obvious that they are not mathematical operations, but the concatenation of strings. When one is a string, the other will be converted into a string for string concatenation. And E is 1 plus NA here. And we can see that when any number is added to NA, NA is returned at the end. The general arithmetic operators have numeric types on both sides. If one of the operators is an addition operator, the result of the calculation is a string. In the example of assignment to C, it will be converted to a string first, and then followed by another character. The strings are spliced together and return to the string form finally. If both sides of the operator are numbers, mathematical operations will be performed. For other operators, we can also write an example to test. We declare the variable a equals to 1 and multiplied by the string 1.1. Then we declare the variable b equals to string 1. Divided by string 1.1 here. And we declare the variable c equals to 5. Modulo the operation. Modulo operation is the meaning of the remainder actually. That is performing a division operation, and the result is a remainder of the division operation. So what kind of result will we get when we perform this modulo operation on a non-numerical type string, the letter A? We use the plot function to plot all these data here. And here we click on backtest. We can see that the plot 0 is the first line, and the plot 1 here is the second line. But there is no plot C as written in our code. Plot C. That is, the output of plot C is always null and not drawn on the chart. The output values of plot 0 and plot 1 are also fixed at 1.1 and 0.91 here, which are the values of A and B, respectively. We can see that even if we use the arithmetic operator, if the operands on both sides have strings of numeric type, then it still does the operation. It will convert the strings of numeric type into numeric values, and then use the operator to perform mathematical operations on both operands. And we can see that both of them return to the result of the calculation. If the operand is non-numeric string, such as a letter or a word, then it will not be able to perform the operation, so it will return to null. And in our code example, the line C here was not drawn out. This is the difference between the Python language on FMZ and on TradingView. The Python language on FMZ is not very strict about variable types, and if the variable passed in a string instead of a number, the arithmetic operator will still work. But if the code is running in the Python language on TradingView, it will report an error. In other words, if both operands of an arithmetic operator are strings, or if one of them is a string, the system will convert the string to a value before performing the operation, except for the addition operator. The addition operator will turn both sides into strings directly, and then perform a string splicing, which requires our special attention. If a non-numeric string cannot be computed, then the result of the system operation is directly null. Therefore, the Python language is a little more fault-tolerant when written on FMZ. Next, let's talk about comparison operator, which is also an operator that we often use when writing strategies. In the previous video course examples, we also used the comparison operator several times. Comparison operators are binary operators that require two operands. There are 6 comparison operators. Less than, greater than, less than or equal to, more than, greater than or equal to. Equal to, and not equal to. The comparison operator is mainly used to determine the size of two variables. Then we use the following example to demonstrate it. First, we declare the variable a and assign it the return value of an expression 1 more than 2. But 1 cannot be less than 2, cannot be more than 2. So a must return to false. And we declare the variable b, that b equals to 1 less than 2. And it must be true here. Then we declare the variable c, let it equal to the string 1 and less than or equal to 2. What kind of operation will it perform at this time? And then we declare the variable d. Compare it with a string again. D equals to string 1 more than or equal to 2. And then we declare variable e, let it equal to 1. Let it equal to 1, where the value of e return to true. E must 1 must equals to 1 here, so it will return to true. And we declare the variable f, let it equal to 2, not equal to 1 here. The result of it will return to true, because 2 must be not equal to 1 here. And we declare the variable g, that is equal to open more than close. This form was open on behalf of the opening price of the current K-line bar. This form was often used in our previous examples, that is, to determine whether the opening price of the current K-line bar is greater than the closing price. If so, it returns to true. If not, it returns to false. Here, the value of g depends on the actual operation of the situation. And we continue to declare the variable h, let it equal to NA more than 1. And the variable I, let it equal to 1 more than NA here. Here we swap the position of 1 and NA, and we observe whether the values of H and I will be different. We print out all the variables by using the runtime log function here. And we check all the information or the code. Here we click on backtest. Oh, it reports an error. Let's go back to the code page to check it. Line 20. Here. C, D, E, F, G, H, I. And we click backtest again to see it. We can see the exact output here. We go to the log information column. We can see that many results are output here. Let's copy the first column to the code page for our observation. We can see that the output of A returns to false, as we expected here, and B returns to true. And the value of C returns to true. Why? Because when the comparison operator performs an operation, if one of the two operands is a string of numeric type, it will try to convert it into a numeric value and then compare, which is actually 1. 1 is less than or equal to 2. In line with the logical judgment conditions, so C returns to true. D returns to false here. The string 1 is greater than or equal to 2. It will first convert the string 1 to a numeric type and then make a judgment comparison. Here 1 is greater than or equal to 2 is not valid, so D returns false here. E equals to 1, 1 equals to 1. The condition holds, so E returns to true here. As for F, 2 does not equal to 1, so F is true. The value of G, the opening price is greater than the closing price when copying, but in fact the opening price is not greater than the closing price, so false is returned here. That is to say, both sides of the comparison operator can also use built-in variables to perform operations on the operands of the operator. What kind of effect will have if the operands were written in NA? We can see that H returns to false here, and the expression written with the comparison operator will return to false if there is NA on both sides. We look at the variable I here, and the position of NA is switched with 1, but I still returns to false here. That is, if one of the two sides is NA, it will return to false finally. As we can see, the comparison operator is very simple to use. It is also the operator we use the most when we writing strategies. It can compare both numeric values and built-in variables, such as open and close in our example. It is the same as the calculation operator. There is a difference about the Python language between FMZ and TradingView. FMZ does not have particularly strict requirements for the type. So, such as statements D equals to string 1 more than or equal to 2 will not report an error on FMZ. The execution will first convert the string to a value and then compare the operation. But on TradingView, it will report an error. Let's move to the logical operators. There are only 3 kinds of them. It is an operator that we often use when writing TradingView Python language, writing strategy transactions, the trigger conditions for placing orders. It is generally used to connect multiple expressions or logic and or and negation. There are 3 logical operators: not, and or. Not is a unary operator which uses only one operand, and the and or are binary operators which need to have 2 operands. Let's start with the AND operator first. If we want to determine whether a k-line is positive and a dodgy, here are 2 conditions. First, it is a positive line, and it is also a dodgy. And here we need to use AND to connect the 2 conditions, so we declare the variable a and assign it a value by using the if condition. Close is greater than open. Proving that the closing price is greater than the opening price. And if this condition is true, then it meets one of the conditions we require. It is positive. At this time, we use AND to connect this goal and that we eventually want to achieve. The second condition is that it also has to be dodgy, and that dodgy is what kind of pattern? Dodgy is that the opening and closing price is very close, that is, their difference in absolute value is very small. We can use a built-in function, mathAbsolute, to find the absolute value to calculate the absolute value of the difference between the opening and closing price. We use the arithmetic operator minus, which we talked about in the last lesson, to construct an expression, which can also be passed in as a parameter. So this place, we can write close minus open. which of course are two built-in variables, that is, to calculate the absolute value of the difference between the opening price and the closing price of the current K-line bar. When this difference is small enough, the K-line pattern is shown like a dodgy state. So the second condition is to determine the absolute value of close minus open. If it is less than 20, of course, the 20 here is artificially specified. If the opening and closing price distance is set very small, then it may be very difficult to determine. So we decide based on this price scale currently tested. A doji in the strict sense means that the opening price is equal to the closing price. But if the price value of a certain variety is very large, it is rare that the opening price is completely equal to the closing price. Generally, the two values are close to a certain value degree. That is, this K-line bar looks like a doji. Then we write if the condition is established. We let the if condition return to true. If the condition is not established, else false. It will return to false. This time the value of A represents the current K-line bar is not the doji. If established, A is true. Otherwise, A is false. Then we use the plot chart function to represent the value of A on each bar. And if A is true, we will draw the chart, assign a string doji to the parameter chart. And we let it drawn on the main chart. Then we click backtest. As we can see, the K-line bars on the marked with dojis here in the backtest charts all show a doji pattern Of course, if we set the value less than 20, the judgment will be much more accurate. Let's go back to the code page. Our code uses the AND logical operator. That is, we use the AND logical operator to connect two conditions and combine the two conditions into one condition. That is, the final expression is true when both conditions are true. We use the logical operator OR to connect two conditions. The logical operator OR is that when one of the two conditions is true, then the expression is true. Here let's write a code to test it. If I want to determine the crossover of two averages, then the crossover is divided into MACD, bearish crossover, that is above the SMA and below the SMA. Here we write a strategy. Test. Specify it on the main chart. And then we declare a variable EMA10. Indicating it's a 10-period EMA average. We use the built-in function TAEMA, use close at the data source, and specify the period of the EMA indicator calculation as 10. We declare another EMA variable, name it as EMA20. And again, we use the built-in function TAEMA to perform the calculation. Use close at the data source and specify the period of the EMA indicator calculation as 20, just same as the above. EMA 20 here. That is to say, one is fast line and one is slow line. Again, we write a condition. We declare a variable a, assign if to it with a condition statement. And use the function TA crossover to determine whether EMA10 and EMA20 are above the SMA or below the SMA. If these two averages are above the SMA, then TA crossover returns to true. We want to determine if A is a cross. Here we connect it with OR. Use the TA cross under function to determine the bearish crossover, and then pass it into the EMA10 and EMA20 parameters. If the condition holds, it returns to true. If not, it returns to false. We use the plot chart function to draw the result of the drawing, And if A is true, the drawing operation will be performed here. And if A is false, the drawing operation will not be performed. We use ternary expression to assign values to char parameter. We use TA crossover function here. If it is a golden cross, we let the value of this expression be a golden cross. If it's a bearish crossover, we let the value of this expression be a bearish crossover. We let the value of this expression and we set the different colors according to golden cross and bearish crossover, using a ternary expression to show red if it's a golden cross and green if it's a bearish crossover. Color red. Color green. Next, we draw the SMAs of EMA and of EMA10 and EMA20 by using the plot function, respectively. Name it as EMA10 and EMA20 respectively. EMA20 here. And we click on Backtest. We can see that these two averages have been drawn on the chart. EMA10 is the yellow line here, and EMA20 is the purple line here. And when they cross, a golden cross is formed here, we can see. which is marked when it was a bearish crossover. This place was also marked. Usually when we write some average strategies, we take this as a signal to buy or sell. Of course, there are times of oscillation. And here is the oscillation from golden cross to bearish crossover and again to golden cross. With this example, we are clear that the OR logical operator is used to connect two conditions. And when one of these two conditions is true, the overall expression is true. Only when both conditions are false, the overall expression will be false. Let's move to the not logical operation operator, which was also used in our previous video tutorials. In the model execution course, we used the built-in variable bar state is history, which was used to determine if the script has been executed to the real-time kline stage. If the script is executed to the real-time kline stage, bar state is history will display as false. If it is not in the real-time kline stage, that is, in the historical kline stage, bar state is history will display as true. We can use an if statement to determine that. A equals to if not bar is history, bar state is history. Which returns to false if it runs on the real-time kline bar, or non-false if it is reversed with not. That is, not bar state history is true. At this point, if A runs to the real-time bar stage, it is true. We use the plot chart function to draw the chart. Pass in A first. Assign a string to chart. Arrive at the real-time kline stage. And let it draw on the main chart. Here we click Backtest. We can see that the result is displayed on the chart. The time we set is a bit short, and we can adjust the time to July 9. At this point, we click on Backtest again. We can see that when it reaches the real-time real-time K-line bar stage. Characters are marked on each K-line bar. Which means that no drawing operation was performed on any of the previous historical K-line bar stages. This is the use of the NOT operator we are talking about, that is, reverse a Boolean value. When it comes to logical operators, then we must talk about truth tables. It is the same as we learned in high school. Here we are testing and learning in a backtesting system. First, we declare a variable a and determine whether it is equal to 1. The result is definitely true here. So this expression is true. Then we declare a variable b. Where b is not equal to 1. The result is definitely false. Then we declare a variable c, where c is equal to not b. That is, b is false, so the result of c is true. Then we declare a variable d, where d is equals to not a. That is, a is false, so the result of d is false here. We use the runtime log function for data printing, and we write the first log as test, the logical operator, concatenated with and mark it in red. Next, we print the specific values, and we start with a. can delete this line. And then we write runtime log function for B. Change it to B here. B and C. B and C. We can add a line of A and B here. Change it to B. And here is A and B. The fourth line is D and B. We change it to D here. B. That is A and C, A and B, B and C, and D and B. In this way, we can see what kind of arithmetic results can be combined for different combinations. Then we test it with the OR operator, also marked in red, in the same way as the AND operator above. We can copy it and change it directly. Change it all here. Change it to O. In order not to overprint the message, we throw an error with the runtime error function and make it stop after printing once. And here we click on backtest. Wait for a moment. We can see that in the log message column, when we test the logical operator with AND, A is true and C is true, then A and C returns to true here. And when A is true, B is false, A and C returns to false here. That is, among the AND operators, if one of the operands on both sides is false, then it will return to false. When both D and B are false, then it will return to false eventually. Then we look at the logical operator OR. When A and C are both true, connecting the two operands with OR operator, it returns to true here. A or C returns to true. When A is true and B is false here, A or C will return to true by using the logical operator OR. That is, if either operand is true, it returns to true. When B and D are both false, B or D, here is D, B or D returns to false. We can go back to our strategy code page. D or B. Here we change the code. It's D and D here. D or B. D and B. And we click backtest again. Wait for a moment. And we can see in the log column here, D or B false, D and B false. We changed this code just now. In the OR operands, in the OR operator, when B and D are both false, it returns to false. In fact, this is a truth table, that is a logical operation based on a truth table. Let's go back to the code page. In order to prevent the backtesting system from printing all the time, we use a stop function to make it stop and easy to observe. In this way, we can see that the truth table is exactly the same as the printed truth table. That's all for today's lesson. If you find our video tutorial useful, don't forget to like, follow, and repost. Your support is our greatest motivation. See you in the next lesson.